Just trying to illustrate how you can produce new vector fields by starting with some known vector fields. Okay. So the next question is, so if these are the vector fields, the next question is, how do we integrate these vector fields? So what I'm going to explain is how to integrate vector fields over curves. That's right. Why would we be interested in this, right? So that's the question. Well, yeah, this is a math class. Come on. But no, seriously, of course we wouldn't be doing that if there weren't a good reason for it. And there is a good reason for it, which I'm going to explain now. Okay? What I mean by this comment is that in math, I'm not trying to say that we do useless stuff. On the contrary, we do very useful stuff, but sometimes it takes a while to really appreciate what exactly this is good for. And so you have to be patient sometimes. Okay? But in this case, actually, you don't have to be patient because I'm going to explain it right away. So this is one of those cases. Okay, so I would like to explain the real problem, which actually will lead us naturally to the notion of an integral of a vector field over a curve. And this is actually very easy to explain. And this has to do with calculating the work done by a force. So, by the way, one important example of a vector field, which I kind of alluded to here when I said force of gravity, I should say it more forcefully, probably, which is that forces in general are represented by vector fields, right? Because a force also has a magnitude and direction, usually. And force pushes you in a certain direction, not only with different levels of strength, but also pushes you in a certain direction, or pulls you in a certain direction. Like force of gravity. Force of gravity pulls me down and not, I'm not flying out of this class, which some of you may have wanted, but I'm staying here. And the only thing that happens is that, well, this floor prevents me from falling down, but if suddenly this floor would disappear, I would go down, right? So I would go down, not up, and not right, not left. That means that the force of gravity, in this case, actually has a very specific direction, down, like the apple which fell on Newton's head, right? So force has a certain direction. Likewise, electromagnetic force and other forces, they are represented by vector fields. And if you have a force, then oftentimes you may be interested in the amount of work that a certain force vector field does in moving an object from one point to another, from point A to point B. Okay? And the upshot is that this kind of quantity, the work done by force, is precisely represented by an integral over a curve, where the curve would be the path along which the force moves the object. Let's say a particle, if it's an electromagnetic field, or if it's a force of gravity, it could be any object you want. So, but to explain why an integral, okay, as always, we have to go back to kind of the elementary situation where everything is simplified, where the force is constant and the displacement is kind of linear, and we look at the formula for the work, and then we kind of average it out over a general curve. Okay, and that's how we get to the integral. So the first question I'm going to ask is, what is the amount of work that is needed to move a particle from, say, from this point to this point along a linear segment with some displacement delta r? If you have a constant vector field, if a force is constant, so force is everywhere constant, like in my first example where it was I, like this. What is the amount of work needed to move particle from point A to point B to be in the constant force vector field? Like this. So in other words, the value of the force is the same everywhere. And actually, it's very easy to illustrate this in the following way. And I will do it, not with a particle, but I will do it with this eraser. You see, this is what I'm talking about. I'm moving this. Unfortunately, I never erased it, but I hope you memorized what was here. Let's do it again. No. So, okay, you see, I'm moving this eraser from this point to this point, and I'm applying force. Now, the most efficient way to do it would be to use for the force to go exactly parallel to the blackboard, right? But in reality, I don't do this because I also want to push sort of against the blackboard. So first of all, I don't lose the eraser, and also erase it better, right? So in other words, oftentimes the displacement vector and the force vector are not parallel to each other. That's natural. For example, I can go like this. So see, there is a component of my force which is moving this way, but there is also a component which goes this way and keeps it close to the blackboard. I can do it like this, or I can do it like this. A stupid thing to do would be to go like this, because then I wouldn't be able to move, right? So in order to do this, I have to have a non-zero component in this direction. But then I can have some component in the transverse direction. So the question is, what is the work that has been done? And the point is that what is essential for this process is not the force itself, but only the horizontal component, the component in the direction of displacement. You see, in other words, the work is equal to the displacement, which is this. Let's just write the word displacement times the component of the force along the displacement vector. In other words, what matters is how thoroughly I raise the blackboard. It doesn't matter how much I sweat doing this, you see. So what I'm talking about is not how much work I have done, but the question is what is the result, you see. And for the result, it doesn't matter how much pressure I was applying towards the board. What matters is how much force I applied in the direction of the displacement vector. So that's why I get this formula. But if so, it means that algebraically, I draw this. This is displacement vector. I can draw it again, right? And so this is the force vector, and this is the displacement vector. Let's call it delta r. And so the work done moving this particle is delta r times f, but not f, but rather this. And this is some angle theta. So this is actually the length of this is f length of f times cosine of this angle, so times cosine of theta. So what I'm trying to say that it is just a dot product between dr and f. That's what I'm trying to say. The work is a dot product of the displacement vector and the force vector in this kind of simplified situation where displacement is linear and the vector field is constant. Okay? Or if you want, you can write it as f dr, f delta r. Doesn't matter. Sorry, I should have written dr, not delta r. This vector. Okay, so that's the idealized situation. And now the general situation will be as follows. I will have a more general curve, not necessarily a line segment. So it will be, let me draw it like this. So it will be like this, let's say. And this will be some point A, or some point A and this B. And at each point I will have some. So you want like this. So you see the vector field changes. It has different values at different points. Like this. Okay? So let's suppose I would like to calculate the work done by this force in moving this particle from this point to this point along this curve. So what should I do? I should break it into small pieces. And this is a typical thing. This should be almost a reflex by now, because this is the kind of thing we always do when we talk about integrals, right? We break it into small pieces. And each small piece we approximate by this idealized situation, where this will be, displacement will be just linear, right? And the vector field will be constant. Because if the vector field varies in a continuous way, in a smooth way, more precisely differentiable, if it is differentiable, right? So then it is a good approximation on a small segment, subsegment here, to think that the vector field actually doesn't change so much. So it's a good approximation to replace it by the value at any given point within this small interval, right? And then the work will be equal to, the total work will be the sum of the work done on each of the small intervals. And this will be the sum of f evaluated at some points along this, within this interval, dot delta Ri. Right? And so you know what will happen. You know what will happen when this partition becomes finer and finer. This sum will converge to an integral. Because this, of course, is very reminiscent of all kinds of integrals we've done up to now. We've done double integrals, and we've done integrals, triple integrals, and many others. And it's always the same idea that if you have an expression like this, where you have a sum over this small, over this kind of partition, then in the limit you just replace this by an integral. And this is valid where if the quantities involved satisfy some natural conditions like being differentiable. And so the result of this is an integral of f dr. I would like to say from a to b, but it would be a little bit. It would not be very. It would not be a good idea to write it like this. You see, when we were in a one-variable calculus, there was only one way to connect point A to point B, because we were going along the single line that we are given. Here we are on the plane, and there are many different ways to connect these points. And of course, the answer will depend on which way I'm going. Right? The longer the path, the longer the work, the larger the work that will be done. Okay? So instead, I will write it like this, where over C, and I don't mean like ABC, but I just want to denote the curve by C, by letter C. So A and B denote the endpoints, but C denotes this entire curve. It is important, however, to remember the orientation of this curve. We go from A to B and not from B to A. If we were going from B to A, the calculation would be different. Okay. So now, now let's talk about this formula. So this was to convince you that integrals of an integral of a vector field over a curve is important. It gives you the quantities like the work done by a force on a certain particle, let's say. But now I have to explain in more detail what exactly this integral stands for. So I would like to explain it in more detail and also give you a recipe how to calculate it. Okay? So let me write it down one more time. It's f dr over c. So for the dot product, we have a nice formula in terms of the components of the vector. So let me remind you that f is a vector field which looks like this. It's p times p of xy times I plus q of xy times j. Right? And what is dr? dr is a vector which is dx times I plus dy times j. So let's take the dot product of these two. The dot product is going to be p of xy dx plus q of xy dy. So in retrospect, the result actually looks very natural, because you see, in the single variable calculus, the only quantities that we were allowed to integrate were integrals like this. Let's say f dx, f of x dx. Well, first of all, there was a function which depended only on one variable because it's a single variable calculus. But also, there was only one dx. We could only integrate against dx because there were no other variables. Now we are on the plane. So there is dx and there is dy. So we could integrate a quantity of the form p times dx, and we could integrate a quantity of the form q times dy. And this is the most general expression which we could actually integrate over a curve in a two-dimensional space. Now we got this by thinking in terms of the work done by a force and by writing as a dot product of the force vector field and dr. But you see, the end result is actually very nice, and we could have actually written this end result from the beginning as the most natural expression, really, that we could think of integrating over a given curve. Again, because you have dx and dy, and then each of them could come with some factor, with some function, which would be some function p and some function q. Okay. So now the only thing that remains is we need to explain how to actually compute this. And this is where the methods which we developed at the very beginning of this course are going to become very useful. I'm talking about, of course, parametric curves. To compute this integral, we need to parameterize our curve. Okay. So to compute, we parameterize our curve C. In other words, the curve was like this, right? But we parameterize it, which means that we're actually identifying it with a certain interval. But an interval and then some auxiliary line with a coordinate which we usually call t. So we identify this curved object, this curve on the plane, with a straight object, with a line segment on this auxiliary line. We kind of identify this point with this, and we identify this point with this, and the points in the middle identified in a certain way. Right? So that there is a one-to-one correspondence between points here and points here. And algebraically, we write it like this. We say x is f of t, and y is g of t along this curve, and we put some limits on t. It's from a to b. So here, the endpoints were actually points on the plane. I could not have, that's why I called them capital A and capital B, because actually capital A was a pair of numbers. It was some, which actually now I can write as f of a and g of a, and this b is f of b and g of b, right? And so let's substitute this in this formula. So what do we get? We will get integral now just over this interval, which is great because this is already kind of integral that we did in single variable calculus. Before it was an integral over this curve. But now we write this integral over this curve as an integral over the line segment by using the parameterization. And it looks as follows. We have to substitute instead of x and y, we have to substitute f of t and g of t. And then we have to write dx in terms of t. But what is dx? Dx is, of course, just f prime dt. Just by the usual formula. Dx is f prime of t dt. And dy is g prime of t dt. So I replace dx, this dx, by f prime of t dt. And then I write the second one, which is q of f of t, g of t, times g prime of t dt. And then I close the bracket. Or if you will, you can write it as a sum of two integrals. This is the first integral, and this is the second one. But you see, I have, by using the parametric form for this curve, I have been able to rewrite this integral, which involves x and y, as an integral in one auxiliary variable, namely t. Okay? So let's see, we have actually 1 minute to do an example of this. So let's say, compute the integral of z dx plus x dy plus y dz. See, and on purpose I'm doing it in three-dimensional space, just to show you that actually everything works out in the same way in the three-dimensional space as in the two-dimensional space. The difference is that now you have three variables, x, y, z, and likewise you have dx, dy, and dz. And so, let's say you have a curve in which x is t squared, y is t cubed, and z is t squared. Okay? And t goes from 0 to 1. So the first term, so likewise for dz, you will have some h prime of t dt, where h is the formula for z. Right? So this will be the integral from 0 to 1. Z is equal to t squared. Dx is equal to 2t times dt. Plus x is equal to, sorry, it was z, that's right, z dx. X is equal to t squared. Dy is equal to 3t squared dt. And finally, here you have t cubed, and dz is 2t dt. So you end up with a very simple integral in one variable. Okay? So we stop here, and we'll continue on Thursday.